Low in-band RCS Reconfigurable Metasurface with LP feed for CP transmission, LP reflection, and simultaneous transmission reflection mode switching. Let's divide into the outline of our presentation. The vision of 6G technology is to integrate satellite and ground communications seamlessly. To achieve this, we've turned to reconfigurable transmission reflection integrated metasurfaces, which enable multi-beam communication. A key requirement is the ability to switch between linearly polarized and circularly polarized beams for ground and satellite communications, respectively. Now, let's discuss the meta-atom design. Our metasurface features a receiving patch for linear polarization and a transmitting patch for circular polarization, enabling LPCP transmission. The receiving layer is divided into two parts for X-pole and Y-pole patches. We've integrated 2-pin diodes on X-pole to achieve 1-bit phase control for reflection and transmission modes. We've achieved variable-sized 1-bit reflection phase control by introducing rectangular branches in Y-pole. 1-bit reflection phase bandwidth is 10.8% in Y-pole. 1-bit reflection phase bandwidth is 12.9% in X-pole. 1-bit LPCP transmission covering is 3.5%. We've constructed a 12 by 12 array with a unit period of 15 millimeters. This array is excited by an LP horn and operates with an F/D ratio of 0.8. Our RTRA metasurface operates in 3 modes: RA mode, TA mode, and TRA mode. To enhance the array's performance, we've implemented the Random Sequential Rotation Technique, or RSRT, which improves the array's bandwidth and radiation characteristics during large-angle scanning. In this slide, you can see the RSRT for the transmitting layer and phase distribution in TA mode for zero scanning, TRA mode unit distribution, and phase distribution when the RA and TA beams are pointed at 0 and 30, respectively. The checkerboard distribution and the encoding for zero beam pointing in the RA mode for RCS reduction. We've also achieved plus or minus 60 degrees beam scanning in both RA and TA modes, which is quite an achievement for our metasurface. Measure results in TRA mode, such as RA, 0 and TA, 150 and so on. Let's take a look at some measured results. We've achieved a 1 dB gain bandwidth of 10.1 to 11.3 GHz and 10.45 to 11.05 GHz in the RA and TA modes, with an aperture efficiency of 19% and 13%, respectively. The 3 dB axial ratio bandwidth is impressive, covering 9.87 to 10.95 GHz in the ZAS plane and 9.83 to 10.7 GHz in the AS plane. In conclusion, our RTRA metasurface not only achieves plus or minus 60 degrees beam scanning in both RA and TA modes, but also improves the axial ratio bandwidth using RSRT. By employing genetic algorithms, we've obtained simultaneous beam scanning for both RA and TA. The proposed RTRA, arranged in a checkerboard pattern, also exhibits in-band RCS reduction characteristics. Thank you for your attention. If you have any questions or would like to collaborate on future projects, please reach out to our email.